Good morning, everyone. Welcome to the second day of the tutorial where I'm going to write a ray tracer in Rust. If you haven't seen the first video, go and look at that. It's short, it sort of covers what I'm doing and what we're trying to achieve. We're following through a ray tracing tutorial written in C++. I found it via some other Rust people that I follow online, and it looks pretty achievable. So the idea is to go through two sections of these kind of 12 main sections here every day, and we should be done by sort of the end of the week, Sunday. I also have a GitHub repo which has all the code that I'm going to be writing and uploading every day. So please, go and have a look at that. Ray_tracer. Links off to the tutorial there as well, and I'll link in the description below. So what we covered in the first video was just this overview section, and then we went through how to output an image using ppm, a plain text ppm file. And we just wrote some simple code that generated this view of a graduated rainbow-looking image. And so today we're going to go a bit further. We're actually going to take section 3 and 4 and start building actually the first bones of the ray tracer, I think. And so the vec class we already started, the vec3 class, in the last video, and then this one we're going to complete that or fill that one out, and then we're going to have a ray class, and then we're going to start actually doing some kind of linear, I think it's called a lerp, where which stands for a linear blend or a linear interpolation, and we're going to use our very simple ray tracer to do this kind of two-dimensional ray traced linear blend or lerp, which is pretty straightforward, but should be possible in about an hour or thereabouts of coding, depending on if we get stuck on stuff. So for those of you that were looking at the code last time, remember we had this vec3 class here. This vec3 class is pretty basic. It might change. I implemented an override for the addition operator so that I can add vectors together. And that's just vec3 plus vec3 and returns a vec3. And then there were probably a whole number of other things that we were going to add there. We had a constructor there as well. In the main class, we set the width and the height in pixels. We have a max pixel value, so 256 colors per channel RGB, so 24-bit color. And then we just call this write ppm function that prints this thing to standard out. And then we were outputting that or redirecting that to a file just to capture it. And so what we'll do is we'll look through and sort of complete the vec class. And a lot of it is, we've got some getters and we've got some other overridden operators here, and then some other kind of utility functions as well. And that's some of the implementation. So this is just simple vector maths. It's not complex maths. If you don't know what a vector is and you don't know the basics of, like, this is sort of high school linear algebra or first year linear algebra at university or college, then just go and have a look at something online. It's really straightforward. I'm not going to explain that stuff. And then we'll start building the ray class. The ray class looks pretty straightforward. It's got a constructor that sets that has sort of two members that are vectors, and then it has this concept of origin, direction, and okay, so that's the origin of the ray. And B is the direction. Okay, so that's the beginning of the ray, and that's the direction of the ray, and then, and I guess direction implicitly has a length too, right? Because a vector isn't just direction; you have a length as well. And so I wonder, I guess that probably changes drawing distance. I don't know. I don't know anything about ray tracing, so I'm learning as I go. And then point at parameter returns. For some float, it returns the origin plus, I guess, the distance along that ray would be how I'd interpret that. Anyway, and then this thing just uses the ray class, and then it uses this color thing. And so color is where the linear interpolation happens, and it's actually, so there's some. We'll go through this, but this generates a unit vector for the ray, and then it scales that sort of from 0 to 1, multiplies it by a half for some reason, and then it uses this because we just want a graduation from one color to white. Basically, it's going to do that by using this formula, which is kind of represented here. So the blend value is 1 minus whatever the current color value is times the start value. So when t goes to 0, when t goes to 1, you end up with no start value and you end up with the entire end value, and vice versa. So that's the blend, right? So you would loop through, presumably, scaling t from 0 to 1, presumably, or something. We'll work it out anyway. And so you end up with this image. So at the end of the thing, we'll have this, right? So let's go. Let's look at the vector class. Well, actually, you know what? Let's look at how we want to use it. And the way that we want to use it is represented in this ray class and also in this color function. So we actually need a ray class. So I guess the first thing we could do is create that. I'm sort of jumping around because I don't want to just go and implement all the methods in vec3. I could, but that's probably going to put you to sleep. And we can do that over time as we need them. So I'll do it just in time, if you like. And then, I think it's more useful to work backwards from the code that uses and exercises that. So anyway, that's why I'm going for. We'll do a new file and call it ray.rs. And this will be our ray struct. And then we'll implement ray, and we'll have a constructor, which looks like this and returns array. And then the ray has two members. So it has a vec3 A and B. So that should be A, which is a vec3, and B, which is a vec3. And then ray should do something just like this, I think. So it'll take, what will it take? It'll take A and B, well, do lowercase. Whoops, they're vecs. Okay, so our ray function will take A and B, which are two vectors. We could do references, but I'll just leave them like this for now. And then ray will be, we'll just be setting that up. So it'll be A is A and B is B. Don't you love Rust? Pretty straightforward. Okay, so that's our constructor. Now, that all looks fine to me. Okay. So, and then what we'll need in here is we'll need to implement two other functions, three actually. So we'll have an origin. And origin takes nothing and returns a vec3, which will be just returning, origin is just A, right? And then we'll have direction, which does the same thing, just returns a vec, which is B. Okay, and then we've got pointer parameter, which takes a float and returns a vector, which will be A plus B times T. All right, so this is where things should start breaking, hopefully. Okay. Now we need to import vec here. And the way that we're going to do that for now is we'll do use create vec3 like that. So that will make, excuse me, our vec3 struct available. And what we probably want to do is implement some unit tests here as well. And we also want to do unit tests here. We don't have any testing at all so far, and so I want to start getting that in early. And so like a unit test could look like this. So what we do is, the standard way of doing that is to say hash config test. And then you typically have a module, and so most of the time that's called tests. So this is a directive to the Rust compiler, and that everything following this will be a bunch of unit tests, and that's all encapsulated in a module. And then you do use super, because we're building a module tests inside the module, in this case, Ray. And so use super glob like that basically says, give me access to everything up in the parent module so that I can call it and test it. And then when you want to run a test, you do you do hash and then square brackets test. And then what you can do is say, you can say function, hang on, let me just close that. You can do function, what do we want to do? I guess test Ray origin. And we'll sort of just stub these out for now. And we'll do function test direction, or do test Ray direction. And then again, we'll do function test Ray point at parameter. Cool. And then inside of each of these, what we're going to do, oh, it's complaining. Expected function arguments. Of course it did. Cool. And then so what we'll do is we'll sort of fill that out over time, and we'll do the same thing. So because I'm lazy, we'll just sort of copy this, and we'll use the same concept in our vec class, except we'll obviously change them. So we'll have something like test vec3 add. And then as we build other operations, we'll do test vec3 multiply, vec3 divide, for example, and so on. So that should be okay. What have I done? Got the wrong thing there. All right. So anyway, so that's kind of pretty straightforward. And so this is just good practice to have your tests at the end of the module like that, and it's great for refactoring. And when you start changing your code, you'll be able to do that with a little bit more confidence, because you'll see when things start breaking as you run your unit tests. And so we now have a new Ray module. So to import that for now, we're just going to do mod Ray. That makes Ray available, and then we'll do use Ray, and then we'll just use that. So then we'll be able to use the Ray. Oh, it's private. Okay, so we'll be able to use the Ray struct. So it's complaining. The compiler is complaining because Ray is private. So Ray, the struct will need to be public, and then also we'll need these functions to be public. So that should be okay. Aha, good. So I need a reference to self. So that's kind of the calling object, if you like, or the reference to the struct that the method is being called on. So so it should be self.a. Self.b, and the same thing here. Self.a and .b. Cool. Now this is where it should start complaining that we haven't implemented multiply. So we haven't got a way of multiplying a vec and a float. And then in fact, we've got add, don't we? Because we built that, so that should work. So for point at parameter to work, we'll need to implement multiply. So let's go and do that. So what we're going to do is go back to our vec class and implement a multiply operation. So we'll do implement ops mul, I think should be right, for vec. Well, actually, it's multiply, but it's for float 32 for vec3. And then what we need in here will be, again, if you don't know how to do this, and I didn't know how to do this 2 days ago, just do something like, Rust override operator, or something like that. And it gives you a whole bunch of examples. These are good, but I just go to the standard ops module, which is this is the trait that we're implementing. Well, it contains all the traits, I should say, that we're implementing. Yeah. Anyway, and so you should just be able to do. You should just go down here and have a look at what you want to be able to look at, what you want to build. So multiply is shown here, and it's pretty straightforward. It's sort of you need to create an output type. We probably don't. Well, actually, you do. You need to create an output type probably, and then you need to create this function. Self is the left-hand side of the operator. Right-hand side is, in this case, they're doing the same type. So they're probably just implementing multiplication of rationals. That's pretty easy. Yep. Anyway, and so what we're going to do is output is self, and then we're going to have a function mul, which obviously is self, and then we'll have right-hand side, and the right-hand side will be a float, and this will return a vector. And then what we want to do, well, actually, you know what we can do? The best way of doing that would be to do, what's the syntax again? I think it's, self output. Yeah. Okay. So I'm jumping all over the place here, but I should do that here too. So this should be self output, and just to make everything consistent, I'll get rid of the underscore. Okay. So that should be okay. And then what we're going to do is, so to multiply a vector, all you do is you take each element in the vector, and when you're multiplying by a scalar, like a float, is just multiply each element at a time. And so this creates a brand new vector, and so we'll do vec3. And then in this case, we're still using this array member, but what we're going to do is do self.e, the first one, so e0, times by right-hand side. And so and we just do that across the elements in the vector, and then we're done. So self.e1 times right-hand side, self.e2 times right-hand side, and that should be it, and we're done. So that returns a brand new vector that has been multiplied properly. And so now you can see that satisfies this, so we can actually satisfy point at parameter now. So we can add and we can also multiply these two things together. So that's cool, that's easy. Now what we could do is actually try running this. So we could do, cargo check just sort of checks everything. There's a bunch of warnings. So we're not using array. Yep, we're never constructing array, that's true. We're never using these methods. And okay, we should have a snake case. So it's sort of trying to follow best practice for us. So we've sort of followed the C++ example, but that's okay. We'll just go with that. And then what else is it complaining about? Hang on a second. What else is it complaining about? Just it's all minor stuff. So if we were to do cargo test, let's see what we get. So we run all our tests, so we can see that all of our empty tests are working, which is encouraging, right? Not following best practice here, but what we'll do is we'll actually start building some tests. So why not do that? So let's actually make some of these tests real. So we'll use assert here, and we'll say assert. We'll just use assert equals, and we'll assert that. We'll create a new vec, so we'll call it, I don't know, what are we going to do? 2, 3, 4, and 6, plus another vec, 1, 1, 1, 4, or 5, let's do 4. And we want that to equal basically, what should it be? 3, 5, and 10. Okay, so what have I done here? It should be okay. What's it complaining about? Huh? Cannot add. I'm using the wrong class. This is going to get confusing. Vec. Vec 3. Okay, so we should be able to add okay. Now what is it complaining about? Okay, cannot use the binary operation equals because we haven't implemented standard compare partial equal. All right, so this is another trait that needs to be implemented for any type or any struct that you want to build where you're applying these operations. And so that's pretty easy for us to do. We could do it manually, but if we needed to override sort of default stuff, but we don't really in this case. So I think all we need to do here is add partial equal to our derive. And so Rust will actually do sort of just a pairwise, I think, for each element in the array, it'll just look for each element to be equal, and that solved that problem. Great. So let's run our test again. It passes. Let's make it fail. So let's say that is definitely wrong. Oop. It didn't work, did it? Okay, good. So so what I did was I just updated vector here, the sort of the answer that we expected, and I made it wrong, and so you can see that test fails. So that means that our tests are working. So good, we've got all that. That all works. Okay, let's try multiply then. So we'll do assert equals, and then we'll do the same thing. So we'll do vec new. What are we going to do? Let's just do 2, 3, and 4 times by using the wrong type again. 2, 3. Let's just go 2, 2, and 2. And we want that thing to equal vec 3, 4, 6, and 8. Okay. Awesome. And then we'll just make that type correct. So this should exercise, what have I done here? Mismatched types. Oh, we didn't implement that. Oh shit. Okay, sorry. Excuse me. It was basically just times a float, wasn't it? I'm an idiot. So in that case, we'll just do this. So that should be right. So that vector times by 2.0 should just give us 468. So let's try that. Yep. Great. If we made it times 3, that should break. Cool. It does. Excellent. So we've got that. Now, the next one we want to implement is probably divide, but let's see what our code wants. So I think we should be able to build the array class completely and have that work, and that looks like it should be okay. If we started using the array class now, we should actually have something that works, I think. And so let's have a look at what this is actually doing. So array is a vector, effectively, or it has two vectors. It has the beginning and the direction, I believe. So it's a function p of t, which is equal to a plus t times b, where p is a 3D position along the line in 3 dimensions. A is the ray origin, b is the ray direction. The ray parameter t is a real number, float, plug in different t, and it moves along the point. Yep. Okay, cool. So that makes sense intuitively, doesn't it? Add in negative t and you can go anywhere on the 3D line. Right. But interestingly though, if you Okay, cool. So the vector, so we don't need to be sitting on the vector. We just need to be able to extend the vector in either direction. For positive t, you only get the parts in front of A, and this is what's called a half line or array. Cool. So that's what that's kind of like a loose definition of what array is, right? It's for positive t. And then the example C equals P2 is shown here. Point at parameter. Right. So that's what point at parameter means. Cool. Yep. Which is kind of what we were saying earlier, right? So that sort of makes sense, I think. Okay. So all right. So we've got array. Now we want to actually turn this into a bit of a ray tracer. And so the point is that a ray tracer, I'm just reading here, sends rays through a pixel and computes what color is seen in the direction of those rays. This is of the form calculate which ray goes from the eye to the pixel. Compute what that ray intersects and compute a color at that intersection point. When first developing a ray tracer, I always do a simple camera for getting the code up and running. I also make a simple color ray function that returns the color of the background. Okay, sweet. So he doesn't use square images. That's why we're using a rectangle so that we don't transpose the thing and get it wrong. And then y goes up, x to the right. That's a convention. It's right-handed. Into the screen is the negative z-axis. Cool. So out of the screen is towards me is positive z. Into the screen is negative z. And so the screen is z or z for the Americans watching this. All right, and then note that I do not make the ray direction a unit because I don't think it makes things simpler. Right, cool. Yeah, I don't think you'd save any space there, right, or any speed, so it's fine. It's easy enough to just create a unit vector anyway. All right, so let's have a look. What do we need if we want to implement this color function? Let's try that first. So what I'm going to do is I was trying to be clever and pull out all of the ppm stuff into a separate function. I'm not going to do that anymore. So I will, hang on a second, let me just get that right. So we want this inside the main body. That should be better. And then I can just get rid of this right ppm. I don't need it. For now, it's just kind of not helping, which is a bit of a shame, but whatever. So we'll kill that off, and then this should break. So don't need any of that. All right, so anyway, so we need to, I'll cheat. We'll do that, and then that should fix all of that. So this should continue to run. Let's just see that, cargo run. Yep, so that gives us standard output that we expect. All right, so what I'm going to do is I'm going to, above my main function, create a new function called color, and I'll follow the convention here, and we'll do it this way. And so color is going to have, so it's going to take, well, according to this, it's a reference to array. So that's what I've done here. R is a reference to array. And then inside of this, we're going to do let unit direction equal, and then something that we haven't implemented yet, unit vector, which would probably be in the vec3 class, but it doesn't exist. You know what? Let's go and build that. I should have done that first. So what we'll need is we've got direction on ray, haven't we? Yep. Unit vector, and then unit direction. Okay, so we'll need some getters here, I think. And then the rest of it, I think we've got. Cool. So what we need is, what's unit vector? I bet you it's one of these utility type functions. Make unit vector. Okay, so we need something like this. So what we'll do is we'll put that in the vec3 class. It's just going to be implemented directly inside here. So we'll just do pub unit vector. Doesn't take, oh no, it does. Takes a vector and returns a vector. Cool. I guess it just takes a vector and returns that as a unit vector. So the way that it does that is it's just v divided by v length. The problem is, pub function unit vector. Problem is we haven't implemented length, or do we have divide? No, we don't have divide. So the first thing we'll need is length. So let's go and work out where length is implemented. Okay, so length is implemented there. And so that will be a member. So we'll do length and it returns a float. And then this thing is going to be something square root. So it's basically the, okay, we'll need self, of course. We'll need that down here, presumably. Well, actually, do we? No. So this actually is just a, it's just a function, not a method. Anyway, we'll need self dot e0. Well, this is going to be a bit of a pain to write out. E0 times by self e0. Okay. Plus self e1 times self e1 plus self e2 times by self e2, I think. Something like that anyway. So it's basically, it's, you know, the first element in the vector squared plus second element in the vector squared plus third element in the vector squared, and then square root of all of that. So, you know, square root of e0 squared plus e1 squared plus e2 squared. Okay, so that gives us length. That looks fine. And now we need to implement divide. So let's go and do that. So implement ops div for a float, right? We're dividing by a float, and that's for vec3. And then what we'll do is we'll have type output is self, which is basically, you know, we're returning a vector. And then we'll need function div, I guess, self. I'm just assuming this is consistent, probably. And it returns this output. And then what it should be is a new vector where e is, let's have a look. How does divide work? Let's have a look. Operators. Okay, cool. So it's literally just divide it. Ah, hang on, that's dividing by a vector. Dividing by a float. So we basically do the inverse of t, and then we multiply it, right? So that's the same thing as dividing by t. So why is that? I don't know why it's done that way. I don't know. Because this is just the same thing as, you know, dividing by t. Anyway, so we'll just, let's see. Let's just do it this way. I don't think it needs to be that way. Let k equal 1 divided by right hand side. And then we'll do self dot e0 times by k, and then self dot e1 times by k, and then self dot e2 times by k. All right, that should be our divide. And I don't know, let's do a divide test. So let's say let assert equals and we want to do vec new, let's just do something simple, 8, 4, and 2 divided by 2 should be the same as, goodness gracious, I'm going to get confused with this different type, aren't I? Like, you'd almost never implement a vec3 because other smarter people have done that, and so we're just doing it because why not? And we're following the tutorial. But there'd be plenty of examples out there that do this well, and you wouldn't need to do it yourself. All right. Oh, what do we got here? Use. Okay, cool. Here we go. Unit vector. Okay. So I wonder if we just pass v dot length. V dot length will move, won't it? Float can't be dereferenced. What's it complaining about? Yeah, value moved. Okay, the easy way of solving this is to implement the copy trait, which maybe is inefficient and lazy, but we'll just do that to get that working, to fix that. Oh, still complaining. Oh, because I was doing a reference. Okay. It'd be great to do references where we can, especially if, I mean, they're only small little vectors and they'll stay on this. Well, does vec stay on? Yeah, it'll stay on the stack, won't it? So it's not going to use the heap anywhere, I don't think so. But anyway, let's see. All right, so we've got a test, we've got a working vec class or struct. Now this thing is complaining. So let's just, I don't know, let's comment this out for now and run our test. Cargo test. See, yep, that'll work. So multiply divide works. Okay, anyway, and what we want to do, now we've got this capability, we can complete our color thing, I think. So we want, all right. So what was it? Was it unit vector? And then it was r dot direction. So unit vector. Unit vector. Let's try something here. What if that? Okay. So we can use a reference there. Cool. So then anyway, and then what is this thing complaining about? Ray doesn't equal copy trait. All right, cool. Doesn't implement. All right. So we'll do derive copy. Well, let's do debug as well. You can see all the Rust experts cringing as I just derive, copy, and clone like that. Okay, cool. So anyway, we've got our unit direction vector, which is good. So direction is not a unit, but we turn it into a unit vector, and then we get that. And then what are we doing? We're doing let t, which is a float, equal 0.5 times by unit direction y. Aha. So unit direction is a vec3, but we don't have a getter. All right, so we need to do that. All right, so let's go back to our vector class and implement these things. So, so what we need is something like this. So it's basically give me, return the first value in the vector, right? So okay. All right. So it'll be something like this. They'll all return float 32, and it'll be literally something like E0 in this case, right? And so that thing, self.E0. And so that's the pattern, right? This is kind of a bit silly, but we're going to just do these getters and setters, and so or these getters rather, and so we'll do 3 of those. Oh, gosh. Okay, this is getting stupid. Okay. We'll do that, and then one of them will be Y, one of them will be Z, and then this will be 1, and this will be 2. All right, so that should be fine. Just put some spaces there. And in fact, I think that's enough. Okay. It's enough for this anyway. So let's go back and do unit direction Y. So we want, what's Y? Okay, cool. Unit direction Y plus 1. How it looks. So we've got T, which is float 32. So this type hinting is something that that the Rust analyzer does in Visual Studio Code. I don't know if I like it. It's kind of good, so it stops you from mousing over and looking at what the thing is or thinking. I mean, it's probably better to keep track of those types in your head, but who knows? I might get used to it. I was using RLS, the Rust language system I think it's called. It gives you a integration with the Rust compiler and understands the AST and everything, the abstract syntax tree that Rust is building. But it's good, but I've been using an updated thing called the Rust analyzer, and it's doing all sorts of other hinting, and it does the type hinting, and it does sort of like at the call site, it sort of hints at what the parameters should be as well. It's interesting. Anyway, so we've got float t, and now what we're going to do is return 1 minus t. Okay. So we're going to do vec3 of 1. Oh no, it's going to be vec3 new 1, 1, and 1 times by 1 minus t. And then we're going to add vec3 new 0.5, 0.7, and 1.0 times by t. I think. Apparently not. Ah, cool, because we need to return a vec. Cool. So this thing should take a direction, take a array which has an origin and a direction. It should turn that direction vector into a unit vector, so from -1 to 1, I think. And then it'll add 1 to that, so it'll be from 0 to 1, and then it's timesing it by half, so it'll be 0 to 0.5. And then it's using that as a way of, remember this lerp function, so it's going to basically graduate from, it'll never get to, so it'll basically, it's going to return this, so this thing is going to be returned as a vector. And depending, I guess, let's have a look at how it's used. So what do we do with it? So once we've got the ray, we then pass it to color. And we get basically the RGB values out of it. Yeah, all right. And so U and V represent sort of the X and Y plane. So, and I is well, NX, in my case, W is kind of from 0 to the width of the box that we want to draw, so up to 200 pixels, 0 to 200. And we go backwards here, so we go, from 99 down to 0, because we've got 100 pixels high. And so what we're doing here is we're saying, this is going to be a sort of a fraction of, so it'll start at 0, so it'll start at, it'll be 0, and then it'll be 1 over 200, 2 over 200, or 1 over 100, and so on. And we use that to basically create a different ray. And so what it looks like we're doing is we're starting at the lower left corner, in this case, which is -2, 1, and -2, -1, -1 down here. And we're basically going to, we're going to draw the origin first, and then we're going to step across and draw, so it'll start up here, sorry. So it'll start at the top left, basically, and then, because vertical is going to be 100. So it'll start here and it'll draw across the screen. And that will be the same sort of color, so it'll be uniformly blue at the top, or a light blue. And then it'll basically step down one, and it'll just scan across the screen. So it's just going to scan starting from the top right, top left, scan across, and as it goes down, the color that it generates will change because the unit vector will change. The unit vector for the direction will change. Yeah. Okay, we'll go through that in more detail. So now we've got this function thing. So what we're going to do is, so what have we got? We've got U, V, and then we want to construct a ray. So let R equals ray, ray. So this is where we need, we need a couple of other vectors, don't we? So let origin equal, and I'm just going to do this, minus 2.0, minus 1.0, minus 1.0. Then let horizontal vec new 4, 0, 0. And then, oh, it's complaining here. Oh, jeez, vec 3. And then let vertical equal vec 3 new 0, 2, 0, and then let origin should be 0, 0, 0. Something like that. Okay, cool. And so then down in here, inside of our array constructor, we can just use origin. We can use lower left corner. Huh? Oh, what did I do? God. So, got that wrong. Lower left corner. So that plus horizontal times by u plus vertical times by y, or v. Same thing. All right, cool. So now we've got that. Then what we need is, we actually want to call color. So we do let color equal color of R. Which is a reference. Awesome. So that should work. And we don't need this anymore. And so what we're going to do is we'll now do, so what it's doing in this code down here is it's implemented indexing, it's overridden how to index into the vector. We can't just do that. It's not like we can do, you know, color 0. That's not going to work for us. So because what color 0 really means is the first element. Well, actually, we've got X, Y, and Z, so we could use that, but that's kind of a bit confusing. So some of these other getters and setters do the same thing, which is why, so the vector3 class is funny because it's kind of overloading a bunch of concepts, which kind of simplifies the code base, I guess, but looks a little bit confusing when you think about the design of the API. And so here it's got, let me just close that. Here it's got, you know, X, Y, and Z. We need RGB. And so what I'm going to do is basically follow the same thing here. And then do R, G, oops, B. And so this is exactly the same concept, right? RGB, when we're using vector for color, will return the red and the green and the blue channel. X, Y, and Z, when we're using vector3 as a three-dimensional position in space, will return X, Y, and Z coordinates for us. Hence the overloading is a little bit confusing. But what we'll do now is, instead of going and using the overridden indexing, we'll just do, I mean, it probably is more readable as well, in my opinion, is we'll do color.r. So we'll basically get the red channel, and we'll do color dot G, and then we'll do color dot B. Right, and so we're basically saying we've got array. We're going to we pass it through color, which does this lerp thing, and then we're just going to get the red and the green and the blue channels, multiply them by this magic number 255.99. Which is not really a magic number, but for floating point will give us a number between 0 and 255 when we multiply it by this fraction, or this, you know, because color is going to be somewhere between 0 and 1, isn't it? Yeah. Well, so color R will be somewhere between 0 and 1 because we're basically just, it's a unit vector. Anyway, and that should be it. So I think that's kind of done. Which is interesting. That was pretty fast. Let's anyway, let's just check that everything looks okay. Okay, so if we run this thing, what happens? Yeah, so we get output. So let's just output this thing again to data out. We should get a new data out. So yep. Okay, so we've still got, you know, 20,000 lines in our ppm file, and we've still got our our metadata there. The data is different. And so let's go and test this. So I've found oh gosh, that didn't work. I found a couple of online online ppm viewers. Let's just see what happens. I don't know if these work. Ah, there you go. All right, so we uploaded our ppm file, and that's the output. So not a very nice viewer, but hey, it is what it is. And so if we compare it to what we're supposed to get, it looks very similar, doesn't it? Let's see if there's a better viewer somewhere. That was the same one, wasn't it? What about this one? Yeah. Okay. So if I go and find my my output here, and I just drag it. That didn't work. Can I just drag it? Yeah. Sweet. Same thing. Yeah, cool. So if I zoom in, I'm running 4K here, so 4K screen, so 200 by 100 doesn't look very big. But if you look at the image, it should be the same thing, and it looks close enough to me. So we've done it. So that's the end of that video. Let's just recap quickly. What we ended up building here was we sort of refactored the main sort of program here, and we've created a color function which does that linear interpolation, and then we've got we've got some new code here that kind of renders that using the ray class that we created. So we're actually doing ray tracing now, even though it doesn't look very cool. We can say we've started building a ray tracer, albeit one that just builds rays and just draws a background color for us. But we're starting to do some processing with that's what I call processing anyway. And the vector class is a lot more filled out. So we've got getters for X, Y, and Z and RGB. We've got a length and unit vector. We can override operators that we need, like add, multiply, and divide in the case of multiply, and divide by a scalar value. And then we've got some unit tests, which is important. And then for the ray class, we did something similar. We've done that, but we haven't implemented unit tests, so maybe we do that next time. So that was pretty straightforward, and so I'm going to stop there. In the next one, though, we're going to go and start with we'll do 5 and 6, which is a bit more interesting. So we're going to build a sphere, and then we're going to do some collision, some hit detection. So we're going to see whether or not the rays hit the sphere, and if they do, I guess we color them, probably. We can test it by coloring red. Right. So if it hits, then we return red. That's what that bit of code's doing, right? And so we'll end up getting a red sphere on our incredibly exciting background that we've already built. That's in 5. So that's just building some objects. It looks pretty simple. And then the surface normals is more interesting. So we're going to build surface normals. And then color them or something. Anyway, we'll learn how to do this. So I'd say that the majority, this looks a bit more involved, right? Oh, that's cool. So what we're going to do is probably spend most of our time doing this surface normal and multiple objects, and we'll see how we go. So that should be a little bit more interesting, a bit more coding going on there. So all right, so thanks for joining. Don't forget, I'm going to upload everything into the GitHub repository here. Please follow along and clone that if you want. And don't forget to like this video if you liked it. I'd love constructive feedback as well. We want to see something different. Want to see more detail or less detail, let me know. And we'll have the next video up in a day. Please join me for the journey, and thanks for watching. See you in the next one.